All right, good afternoon. We have 3:30, time to get moving. Raise your hand if you had a chance to get to lab or recitation yet this week. Almost everybody, maybe some still scheduled for this evening, yes? Okay, so again, the purpose this week of lab and recitation is just to give you guys a chance to meet your lab and recitation TAs. Okay, that's it. Kind of coverage of new course material starts next week. Okay, so those should get you geared up and ready to go. Wanted to point out a couple of things on the pilot page. Homework number 1 and MATLAB homework number 1 are posted. Okay, and where you can find that stuff is under the content. If you look down here, homework, okay, on the content browser, there they are. They're just PDF files. Okay, and so the homework comes out of the textbook. So these are just a half a dozen problems. The answers to, I think, mostly odd-numbered problems are in the back of the book. This is the revised preliminary edition. The answers are generally correct, not guaranteed. Okay, and so, but that's a resource for you. Obviously, you can ask TAs when you don't buy the sanity check on your numbers as well, or your peers. So anyways, it's about 6 problems a week is what we'll assign. Homework, again, is due at the end of next week, 5 o'clock p.m., 1 week from tomorrow. Okay, so the idea is the homework assigned every week will cover what we covered that week. The whole next week, we're covering new stuff. The homework you're working on, what you'll be going over in recitation with your TA, will be the homework from the week before. All right, so it gives you a chance to really go back and soak in on it. So you go back and look at lecture notes. You guys can tell, again, I mentioned last time, we're doing HD video of this. We'll get the videos up on Pilot, I believe. It's also going to be out on iTunes U. So, I mean, ball's in your court. Something you don't understand, you can go back and look at it. You don't like my explanation, that's why I got a staff of the best TAs in the building, best students on campus to help you guys out. All right, so you can come and do that all next week. The MATLAB homework, haven't taught you how to use MATLAB at all. Not specifically going to teach you in here how to use MATLAB. Okay, so we talked about this before. Hey, what MATLAB is, engineering analysis software. The textbook we use with the class right here, designed specifically for brand new direct from high school freshmen without any calculus background, without necessarily any physics background. Okay, but just like what we do in this class, this content is chuck loaded with physical examples. Okay, and so it's nice. So, you read what it says, read chapter 1. Okay, so it's going to tell you what it's about. Using MATLAB on our computers, okay, all the logistics of how do you get up and running, how do you use the different windows and all that, the TAs are going to go over it, right? In recitation next week, play around a little with MATLAB if you want. It's on the computers in your dorm, it's on the computers in the public cluster, it's all over the place. We'll make an announcement. You can, as an engineering student, you can download the full professional version of MATLAB, software that costs thousands of dollars if you're an industry person who wants to use this. You get the whole professional version on your own computer. Put it on your laptop. Okay, so you just need an internet connection to ping the license server, I believe, and then you're good to go. Okay, and so it's really a great resource. It's used throughout the curriculum. So a lot of self-study, but what you also see is in lab, every single lab assignment, you're going to use MATLAB for something in the lab. Okay, in addition, we'll have 2-hour, kind of intensive MATLAB instruction on 4 different occasions throughout the term, and that portion of the lab is what the MATLAB final exam will be based on. Okay, one point I wanted to make, just being crystal clear, and I don't want to over-harp on this, but I'm going to go ahead and do so anyway, which is this guy right here. Reminder on academic integrity. Okay, and so it is the policy of this course and in general the College of Engineering that we want students to work collaboratively on things like homework. Right? We want you to work together in groups. We want you to learn from each other. Okay, but very specifically with something like computer assignments, working together does not mean you write the code for this problem and give it to me, and I'll write the code for that problem and give it to you. Okay, that actually is how it works in the real world. You're on a team of people who need to solve a problem, you can divvy it up. In school, you got to do your own work so we can assess whether you're learning or not. And if you represent your work with somebody else's work, that's a violation of academic integrity. Same way, if you give your own work to somebody else, you're just as guilty as the person that takes it. Okay? So, stealing a completed MATLAB printout, right? Providing exact pieces of code to somebody else in an electronic way with a cut and paste by leaning over somebody's shoulder and just plain copying it down. Any of that kind of stuff is easy for us to catch. Okay, and if we catch that happening, we will pursue that through the university's academic integrity policy, and you don't want to deal with that. Okay, so most important thing, if you are uncertain about a certain behavior that you're going to do related to any of the homework, just check with somebody. Right there, pull out your phone, fire an email to the TA. Sitting in a group right now, this is what somebody asked me to do. Is this a violation of the policy? Right? Just ask. Total transparency is what you want. Okay? In general, we want you to work together. We want you to learn from each other. We don't want you to copy somebody else's stuff. Okay? It's the bottom line. So after you've been a student for a while, it should be pretty clear. I bring it up so much on MATLAB because we have had organized attempts, 20, 30 students at a time, to turn in MATLAB homeworks completely copied, sometimes in a really not smart way, like the exact same timestamp down to the second. Right, so that kind of stuff, but just don't do it, right? And really the biggest reason, not just for your own character and integrity, but you're not going to learn unless you actually do the stuff yourself, right? And the stuff we have in this course is the foundation for you to be successful in the engineering program, and if you cheat your way through it, you will cheat yourself out of a successful completion of a degree, okay? So don't do it. That's the last I'm going to harp on academic integrity until we catch our first case of cheating, and then I'm going to harp on it again. Okay, so we got 308 people enrolled. There's going to be people cheating. We got 17 people watching out for it, so just don't let it be you. All right, so before we move forward with new material, I want to talk about the schedule that we didn't get to last time. So everybody get a copy, I think, of the course schedule. Important stuff. And I guess since I have this up right now, I can go to, let's see, the content here, course information, and we got a schedule right there. Okay, and so we'll just go ahead and pull it up here in case you forgot to bring this with you. Okay, and so some really important dates. So number one, this lays out week by week all the stuff we're going to do in the course. Okay, and so application of algebra in engineering, straight lines, quadratic equations, all the time we have to spend on that ends today. Okay, fortunately, this stuff is prerequisite kind of math placement level in order to be in here. So what we're trying to do is connect back to some of the things that you might be rusty on, but at least we know everybody's seen this before, right? And so we'll do some more of that today to keep getting our feet wet. And the first homework is just straight lines, quadratic equations in engineering. Okay, let's see, Monday. Right, Labor Day, university closed, so don't come to class, okay, if you have class on Monday in your other classes. Okay, and let's see, week 2, trigonometry. Okay, again, you need to have background in trigonometry to even get in here. So what we're going to attempt to do is set trigonometry in the context of engineering, okay, and really try and cover all the really important stuff about trigonometry in 2 80-minute lectures. Okay, and I'm pretty sure we can pull that off. So we'll do that next week. And then we'll apply those things into vectors, two-dimensional vectors in engineering. If you've had some physics, this word means something to you. If not, this is a brand new concept. That's okay. Okay, then we move on to complex numbers, right? Things like imaginary numbers. We'll even see a little bit of that possibly today. Okay, and how we actually use that stuff in this building. Moving on, weeks 5 and 6. Okay, sinusoids and signals, systems of equations, matrices in engineering. Okay, and in between here, Friday the 20th, if you drop a class without a grade of W, you can do it by the 20th. So basically, no record on your transcript that you were ever in here if you get out by the 20th. And then what happens here is the last homework for exam 1 is based on week 4. Okay, that homework is due at the end of week 5. Okay, it'll be returned or available for pickup from your TA early in week 6, and the exam that covers, essentially weeks 1 through 4 is right here, October 2nd. Okay, we will hold the exams in gigantic lecture halls that seat like 400 people at night on Wednesdays. Okay, we understand some people will have like a chemistry lab at that time. We will have makeup procedures, okay, for people that have academic or professional conflicts with a certain time, as well as for, unpremeditated emergencies my car wrecked on the way, I was violently ill in the hospital, bring the doctor's note, these kind of things. So we understand we got to try and get you all together. It's 4 sections, 308 people. We're not making 4 different exams up, okay? And so we're going to get the bulk of everybody all in one room and do this at once. Okay, so we'll provide very clear details on how to deal with it if you have a conflict here at least a week or 2 before the exam. All right, then moving on, all the way up to here. This is all kind of non-calculus topics. I don't like to use the word pre-calculus because some of this stuff is things that occur after calculus or not at all in calculus. Okay, but then starting in week 7, we move into the calculus portion of the course. We do derivatives for a couple of weeks. Okay, and then after we're done with derivatives, right, we've got the last day to drop with a grade of W. By this point, you'll have had an exam grade back. You'll have had a whole bunch of homework back. You'll have had some laboratories back. You'll have a decent chunk of your grade. And you'll be able to make an assessment of, hey, if I'm doing great in the course, I'm not worried about dropping the class. Okay, if I'm doing poorly in the course, you can ask yourself why you're doing poorly in the course. All right, and if you look in the mirror and go, well, it's because I'm not turning in the homework and I haven't gone to office hours, but I basically understand what Klingbeil is talking about, well, then I would say, well, then it's still time to make a change. All right, change your behavior, get the course completed. If you're at this point and you sunk yourself so far that it's like, hey, I have no idea what's going on, and honestly, I'm not interested in putting in the effort to change that. If that's true, get out when you can still get a W, doesn't affect your GPA. Get back in the spring, okay, and give it another shot at that time. Okay, so just a heads up, that's not until October 25, so lots of time to think about that. Okay, we typically do not have a large drop rate in this course. I'm guessing we'll have 280 plus people still after the drop date. Okay, let's see, week 10, week 11, we are moving into more calculus. Okay, and so integrals. Integrals in engineering, integrals in statics, dynamics, electric circuits, all these applications. And then finally, the last couple weeks of the course, with a couple of lectures right before Thanksgiving, we'll wrap up this 3-week period, really 2 weeks plus 1 lecture before Thanksgiving on differential equations, which is, it's a math course that requires already in college. You've taken several calculus courses before you can take that. Okay, and so we cover this math everywhere from pre-calculus, lines and quadratics, all the way through derivatives, integrals, differential equations, and we do the whole thing in one term. Okay? But what you want to keep in mind is we are not going to get you guys mired in all the trees. Right? This course is about providing for you the forest of why this stuff all matters in engineering. And then what we've gone and done is picked out all the most important trees. Okay, all the important applications that you're going to see over and over again, or applications that continue to reinforce the same math topics. Okay, so when we're doing lines and quadratics now and trigonometry next week, you'll see that in weeks 10, 11, 12, wow, I'm using that quadratic, I'm using that trigonometry, right? If we're not going to use it for real in engineering, we don't cover it in this course. Okay, that's the bottom line. All right, so that's it. And then finally, you make a note, final exam. This final exam is scheduled during the unscheduled final exam block. Okay, and that is done on purpose so that nobody has a conflict with a block final in any other course. Okay, or for a final in any other regularly scheduled class. So for the final exam, we expect very, very few makeups. These would be emergency type situations only, and that's it there. Okay, keep in mind, 2 midterms are nighttime. It's just too hard to find a room we could put 308 and do this if we don't do it at night. Okay, if you're not a night person and that really bothers you, here's your chance to make it up. Okay, final exam is smack in the middle of the day. All right, 12:30. You can get a good night's sleep. It's at Thursday. It's towards the end of finals week. You'll have the whole week to really dive into office hours with the TAs. We hold review sessions for all these exams with the TAs. So really, huge opportunity in the final exam to come back and make the grade you want to make. Okay. All right, and any questions about the basic course schedule there? All right, so I want to talk a little bit then about lab. Okay, here's what we're doing in lab. This week, intro, meet the lab TAs, not a lot of content, 0 content. Starting next week, we do lab 1, algebra and engineering. We've got circuits type lab to illustrate lines, quadratics with things like voltage and current. Okay, in lab 2, you'll look at trigonometric relationships. We use what we call 1 and 2 link robots. Okay, we're talking about links on a board, okay, but a way where you can physically measure all of these trigonometric relationships that you may have learned about in high school, okay, and really start believing why this stuff works. Okay, and then finally, over here in week 4, we'll start with a MATLAB supplemental. And you'll do quite a bit of stuff, almost 2 hours of MATLAB instruction by your TA, and you'll do a whole bunch of MATLAB kind of calculations that most first-year engineering students are not doing by week 4. Okay, so that's a big advantage. Lab number 3, we move on to harmonic signals. Lab number 4, systems of equations in engineering, 2-loop circuit, and then more MATLAB supplements. Okay, that's week 7. After that, we move on to derivatives. We've got a free fall type lab we do for derivatives in engineering. Okay, follow that with some more MATLAB supplement. Then we move on to integrals in engineering, work and stored energy in a spring. Okay, and we finish up with the 4th MATLAB supplemental. Okay, and then the last 2, both differential equations labs. Okay, and so finally, key point, no lab the week of Thanksgiving break. That said, if you have a Monday lab, already you're missing lab this coming week, and so you're off a week already. So it's up to the TA how they're going to handle this. I wouldn't be surprised. There is school Monday and Tuesday of Thanksgiving week. Wouldn't be surprised if the Monday TA would schedule a makeup there. The other option is if you've missed lab, okay, I talked about on the syllabus last time, right, the completion of all labs is required. You can't just say I'm not doing one. It's up to you to figure out when you and the TA can get together and get this thing done. So that week right there on the Monday or the Tuesday, getting with the TA to do a makeup would be pretty smart. Okay? And so finally, right here, during week 15, okay, which is really 14 instructional weeks, so most of this week's gone. This is the last week of classes. We will have MATLAB finals that occur during the regularly scheduled time. Okay, and we'll talk about the logistics for how we're going to pull that off. Okay, but it's going to be every single person sitting down at a computer by themselves and performing things that are based on the MATLAB content of the course. Okay, the exam will be designed so that if you've done all your own MATLAB work and you can, feel comfortable in front of MATLAB, we're not trying to trick you. We're not trying to separate the A's and B's here. Okay, we put this in place to basically guarantee that we have honest participation in people learning to use MATLAB in this course. And when you put in a MATLAB final that is worth 5% of the grade, this is on the syllabus, okay, this is half a letter grade right here. So if you decided that you were just going to blow off MATLAB in this course, okay, what it would do is it would cost you half your homework grade, and then it would cost you half a letter grade on the MATLAB final, and then it would cost you on all the labs. So you really got to embrace the idea of, yeah, I'm going to learn MATLAB when I'm in here, and you're going to appreciate it as you move forward. It's super powerful stuff. Okay? All right, so final thing I think I pointed out in the syllabus, but just connecting back to these dates. In the end, the grading is attendance is 5%, right? Mandatory attendance, 1% deducted for everything that you miss unexcused, up to a maximum of 5. Number 6, you need to get out of the class or you're going to get an F. Homework, 10% of the grade, exam 1, 20, exam 2, 20, final exam 20, MATLAB final 5%, and then the labs themselves, the completion of the lab assignments, including the laboratory abstracts each week. That combined portion is 20% of your grade. Okay, and so that's it. Grading scale, I think I commented on. 2-digit grading, standard university scale is what we do. Yes, question?
The Monday lab that isn't me, do you know if we will begin the second week of lab with the first lab?
Yeah, we'll do the labs in order. So if there's no Monday lab, if you're in Monday lab, then you don't get your first lab till the 3rd week of school because we've got Labor Day. Okay, so you'll be off. So what I think is, we'll talk about the staff meeting tomorrow, but I think we'll probably have to use that Thanksgiving Monday for the Monday labs to get caught up. Okay, so either way, the university is, classes are running Monday and Tuesday. Thanksgiving break starts Wednesday. We good with that? Other questions? Okay, so that is the course schedule in a nutshell. Okay, and so what we're going to do now is move on. More lines, quadratic equations in engineering. All right, so last time we did a problem, I think it was a vehicle braking, okay, and we illustrated the idea of equation of a line. Okay, I'd like to mix up the applications a little bit more. Let's get one more line problem in, then we'll move on to quadratics. Okay, and so for those of us that are double E's, I want to do a circuit problem next. I'll reiterate the idea that no matter what kind of engineer you are, all engineers take circuits. In biomedical, you have your own series, bioelectronics. It's circuits. The guy that teaches it is a double E, actually. Okay, and in mechanical engineering, we send the kids over to double E 2010 circuits as well. So circuits, as an engineer, it's part of the bread and butter of what we do. Okay, and so this is still lines. Okay, but an example, this is from double E 2010, which is circuits. Okay, so circuits 1. Okay, and so here's an example. Let's suppose that I have a voltage source. And I'll talk about what that is in a moment. Okay, and I have a closed loop circuit, which is essentially a wire going all the way through that includes some electrical components. The plus or minus on the left is my voltage source. I'm going to call that V sub S. The S is just a subscript for this variable, voltage source. Okay, this guy over here, the squiggly line, is a resistor R. Okay, and this guy over here is an unknown voltage that I'm going to call V. Okay, so when I build this circuit, this type of thing you'll be doing in the first lab, you will actually connect wires, right, and you can connect a voltage source. So who can tell me, this is what's called direct current here. Okay, who can tell me, what would be an example of a voltage source? A battery. Okay, so maybe this is a 9-volt battery. The plus or minus is like the plus or minus on your battery. It's that simple. Okay? What about this guy? Anybody know what a resistor does?
Restricts the flow of electricity.
All right, that's good. It restricts the flow, so resists the flow of electricity. What does it physically do? Anybody have a physical sense for what happens in a resistor? Say what? It heats up. Right? It burns power, right? So it's like, anybody have an electric stove here? The coils on the top of the electric stove, basically resistors. Okay, anybody know the physical unit of resistance? Ohms. Ohms, pretty good. Raise your hand if you had some kind of circuits in a high school physics class. Okay, not as many people as had physics. Okay, raise your hand if you had any pre-college engineering of any type, like a project Lead the Way or a class that had the word engineering in it. All right, so we're getting more of this. Didn't used to see that much 5 years ago. Great, so ohms. Okay, so somebody that knows what an ohm is, tell me like I'm a 2-year-old. What the heck is that? What's a lot of ohms as opposed to a few ohms?
A lot of resistance.
A lot of resistance. Right, give me a number is what I meant. Do we have any like common devices that we look at it and it'd say, yeah, that's this many ohms? A multimeter. Okay, so that's not a common device. That's an engineering piece of equipment. That's great, though. We got those in the lab. But speakers, right? So what's typical ohms on bookshelf speakers?
8 ohms.
8, pretty common number. Okay, so we're trying to get you just a sense for these are basic things, just like the rest of, what about this? Voltage source, what unit is that? Volts. Okay, so like a 9-volt battery. Okay, yeah, so right here, I've got this resistance, okay, and what happens here is that if I have plus or minus and I hook up the wire, I will get the flow of electricity, okay, and it'll go around the loop, okay, and what we're going to use to designate that is the letter I. Anybody know what I stands for? That's current. All right, what's the unit of current? Amps, short for amperes. Okay, by the way, double E's are typically smart people. Okay, which is why they represent some of the most conceited of engineers and physicists, right? So most of the units are all like named after themselves, okay, and all the laws are named after themselves. Now, the mechanical engineers do that too, right? Like Isaac Newton, Newton's law. All right, so I've got amps over here with current, I've got ohms over here with resistor, unknown voltage in volts, voltage source like a battery also in volts, okay? And so it turns out that when a current goes around a circuit, what happens is every time it hits an electrical element, the voltage changes, okay? Anybody can tell me physically what is voltage? potential difference. Yeah, so we're getting a little past where we need to be really to do circuits problems, but really getting a physical sense for this potential difference. The word potential means electric potential. Okay, so it's the ability essentially to drive the flow of electricity. Okay, and every time I go across a circuit element, I get a change in that ability to drive the flow of electricity. Okay, and it's got to be balanced, you know. So if you're sitting here, you're a mechanical engineer or biomedical, and you're going, really? All of this circuits, a lot of the basic ideas are the same, right? Like if I have a mechanical system, I got to balance things to keep the teeter-totter level. In a circuit, I got to balance things also. Okay, and so what actually happens is, if I go around, I go from minus to plus, that's what we call voltage rise, right? And then when I come down across over here, across the resistor, I go from plus to minus. And there's a certain voltage change across a resistor. I'm going to call that V sub R. Does anybody know if I have, right, a value of a resistor and a certain current here, what is the voltage drop across a resistor? It's I times R. Okay, so let me give you a sense of this. If you're sitting here going, I've never had physics, and why do all these people know this stuff? Okay, I'll try and put it in context for you. VR equals I times R. Okay, this is like, kind of like the F equals MA, okay, if that rings a bell to you. Even double E's are comfortable with the phrase F equals MA. Okay, even MEs are comfortable with the phrase V equals IR. Okay, it's a basic idea that if I have current flowing through a resistor, that I get a voltage drop, it's equal to I times R. Okay, this is named after the guy that came up with it. This is called Ohm's law. Okay, so that's a basic law of electricity, describes the voltage-current relationship across a resistor. Okay, so what do we have here? All the unknowns. I got Vs. This is the applied voltage source. Okay, and the units of that are volts. Okay, and so it's V for volts. Okay, I is the current that flows as a result. Okay, and you guys told me what the unit was for that. That's amps, okay, which is just the letter capital A. Okay, and R is the resistance. Okay, and that's what resists, right, the flow of electricity. Okay, and that is measured in ohms. Okay, and the symbol for that is the Greek letter omega. Right, a capital omega is a symbol for an ohm. Okay, and then finally V is an unknown voltage. Okay, so these are the physical quantities that are going on here. Okay. All right, so turns out that the balance I was talking about before in a circuit, okay, is the whole idea that, you know, if I'm at this point in the circuit, the voltage at this point is whatever the voltage is. If you want to say the voltage is all relative to this point, you can say, well, this is where it's 0. Okay, and if that's true, then when I go here, the voltage rises, it's a different number. And then when I come across the resistor here, it drops by an amount IR. And when I come across here, this would be a plus or minus also, it would drop back down here. Right? And the idea would be, neglecting the resistance of the wire itself here, that I'm on the same level now. Right? So the statement is, if I go all the way around in a circle in a circuit, I got to end up back where I started. Okay? Even a mechanical engineer can understand that. Right? And so that's it. So what we want to apply for a governing law here, okay, that will give us what we're looking for, okay, is essentially the following. It is Kirchhoff's voltage law. Okay, and what that is, Kirchhoff said that the sum of the voltage rises, and in fact, I don't want to write this out anymore, so we're going to call this KVL from now on, Kirchhoff's voltage law. Okay, and it is the following. The sum of the voltage rises is equal to the sum of the voltage drops. Okay, and if you think about a rise as a positive number and a drop as a negative number, then this is the same thing as saying the sum of all the voltages would equal what? 0. Okay, so whatever way you want to think about it, same thing. Okay, very much like if you've had some physics, if things are in equilibrium, then if I add up all the forces, I have to get what? 0. Okay, so it's the basic idea still of balance. All right, and so that's it. So voltage rises, voltage drops. So let's go ahead and do this. Let's start right here. I go from here up to the top. The voltage rise is what? It's this guy, Vs. Okay, so Vs is a rise. When I continue around the circuit, I go plus minus, that's a drop. I go plus minus, that's another drop. So the next two are on the other side. All right, so the next drop is equal to what? VR. We'll write VR. And the next one? V. Do I know what VR is? Yeah. Ohm said, hey, but this guy, I know what that is. This is I times R. Right? And so the statement is apparently that Vs, okay, is equal to I times R plus V. Interesting. So let's say that I think about the voltage here as a function of the current. All right, so last time we talked about velocity as a function of time. What if I think about voltage as a function of current? What kind of function is this? What if I write it this way? Vs is equal to R times I plus V. Does this not look like Y is equal to mx plus B? Right? So this looks nothing like a vehicle during braking, right? We talked about last time. Turns out the math is exactly the same, right? And so really, in this case, this is my Y. M, the slope, is really my resistance, R. Right? The x over here is the current I. And B, the y-intercept, is the unknown voltage source. So, given that, can we answer some physical questions about this just like we might do in lab next week? Okay? And so here's the question. What I would like to do is find the values of these two guys, the resistor and the unknown voltage. Okay, so find R and V given the following. Okay, and so what I could do is I can go into the lab and I could take some measurements. All right, and I could record those measurements as follows. Here's Vs, and this is in volts. Okay, and then I will have a value for the current, I, and those guys are in amps. So let's say, for example, that when I have 10 volts, okay, that the current is 0.1 amps. Okay, and let's say if I have 20 volts, that the current is now 1.1. So I got two values of voltage and current that for this circuit apparently satisfy this equation. Vs equals R times I plus V. So if I had the equation of the line, then the slope would be equal to what? Trying to find R and V. Right, but if I had the answer for the equation, then the slope of that line would tell me what? It would tell me R, right? And the y-intercept of that line would tell me what? That would tell me the V. Okay, so this boils down to, can I find the equation of a line given two data points? Same question we asked about the vehicle during braking. All right, so help me out. What's the first thing you do when you want the equation of a line? Slope. Okay, so we'll start with the slope. Okay, and the slope is m in general with y equals mx plus b. This is delta y divided by delta x. Okay, and so for our problem, right, the M is actually what? R, and the Y value is what? It's the VS, right? So this is the change, delta VS, divided by the change in the I. Remember before I asked you what's an ohm? You guys said, well, it's you know, the amount of resistance. Somebody give me another definition of an ohm? Yeah, it's a volt per amp, right? So if you get a better feeling for volts and amps, volts, it's a battery. What about an amp, by the way? What exactly is that? What do you mean by a flow?
It's like the rate of speed at which charge moves through the circuit.
The rate, the speed that the charge moves through. So anybody know what a physical unit of charge is? Yeah, it's called a coulomb. Okay, so you can think about electric charge like associated with an electron, right? So how many coulombs are going per second? That's what a current is. That's what an ampere is. Okay, so that's it. So really, resistance could be thought of as a derived quantity, right? It's how many volts per amp, okay, that I'm resisting. All right, very good. All right, so let's calculate it. So what does the delta mean? I do what? Subtract the numbers. And so what do I subtract? 10 from 20, 20 from 10, what do I do?
20 minus 10.
20 minus 10. Does it matter if I do 10 minus 20? Long as I'm consistent. All right, so we'll do final minus initial. We think about the second one as final. Okay, that's interesting, right? Because when we think about changes in time, final and initial mean something to us. There's no time scale here. This is voltage as a function of current. I could write that table however I want. Okay, so keep in mind like what's arbitrary and what isn't. Okay, this is arbitrary, which one of these guys I write down. Okay, so we'll call this final and that initial. And so we'll be consistent. Change in voltage, 20 minus 10, divided by change in current, easy numbers, 1.1 minus 0.1. Okay, and so what do you think? What's the value of R? 10. So R is equal to 10. Does that have physical units? 10 ohms. Okay, so go ahead and box that since we were asking to find that. R is equal to 10 ohms. Again, the symbol over here, right, is the capital Greek letter omega, right? That is the unit, the symbol for the unit of ohm. Questions on the slope there? All right, so now that I have the slope, if I want the rest of the line, write down what you have. Vs is equal to 10 times I plus the unknown voltage source V. How am I going to find the V? Rearrange and plug in. What am I plugging for what variables? Okay, the Vs and the I, right? One of those is my X, one of them is the Y. If we think about this, in terms of a point, so using like an XY point, X is the I, Vs, right, is the Y, so we'll write it as I comma Vs. I can come over here and I can use which set of points here? Either one. Why can I use either one? Because they what? They're on the same line, right? They're on the same line. Either point will work. Okay, so we can use whichever ones. I can stick with the same point if I want. Okay, and so we'll go with the 0.1 for the I. Okay, and for the Vs, we're going to go with 10. Okay, and so Vs is 10 times I plus V. Okay, so the Vs is 10. This is 10 times I. I is 0.1 plus V. Okay, and so in one calculator punch, or not, in our head, can we come up with the volt? Yeah, the unknown source apparently is a 9-volt battery. Okay, 9.0, and that is volts. All right, and so then the equation of the line overall, if that was the question, would be Vs is equal to R times I plus V. So 10 times I plus 9, and then you'd want to write units on the entire thing, volts. Excellent. Questions? All right, here's a question for you. We're going to get on to quadratics pretty quickly here, okay? But I want to look at this one other way. Raise your hand if you've done some circuits like in a lab at all in high school or college somewhere else. A lot of people. All right, so even maybe what we're going to do in a lab next week, okay? The way this is written out, which one of these things is the independent variable and which one is the dependent variable? Everything else? So is M the dependent variable?
Oh, no.
Okay, so let's be more specific. So the way this is written, what's the dependent variable?
Y.
Vs or Y. Okay, now, coming out of a high school education, I got this drilled into my head that X is independent and Y is, dependent. Okay, X and Y are just two letters, right? It's made up. Saying one's independent, one's dependent, it's made up. Can somebody tell me what is an independent variable? What does that even mean?
It's a variable that controls something. Like if you increase this one, it will cause an increase or decrease in another.
So she said it's the variable that controls something, sort of. Okay, go ahead.
It's going to be constantly changing, where the other ones are going to vary according to how the independent changes.
Okay, that's on the right track. Anybody else want to volunteer or something? All the way in the back?
It's the one that's manipulated to test over the
It's the one that is manipulated. Okay, so it's the one you get to choose, right? Anyone else want to add to that?
The independent variable would be like the input.
Okay.
Would be the output.
I like that. That's a very engineering way to think about it. Look, the independent variable is the arbitrary one. You choose what it is, you provide it, it's the input. The dependent variable is what results, which is kind of what you were saying, right? It results from that, it's the output. It is calculated from, right, the independent variable. So, this is the way this is written. The whole idea of slope, y equals mx plus b, y-intercept is all based on the idea that the left-hand side, okay, is the dependent variable. Now, back to the question that I asked. I go to a circuits lab. What are you more likely to do when you build a circuit? Okay? You're more likely to hook it up to a battery and measure the current, or apply a current somehow and then measure a battery. Or maybe you have no feeling either way. I don't know. Anyone? Apply the voltage. I mean, even the terminology, right? Voltage source kind of implies that I'm putting the voltage as the input, right? This input-output idea. So I took something that physically seems like this is the input and the current is what results as the output, okay? But when I wrote the equation, it's kind of the other way around, right? I mean, this looks like the input and that looks like the output. So maybe if I'm an experimentalist, that bothers me. Okay? And so I want to go into the lab and I want to take this data, but the way I want to take the data is actually more like the way the table's written. This should be the X. That should be the Y. I apply this battery, I measure that current. I apply that battery, I measure that current. Can I do the problem that way? Or if I try and do the problem that way, am I going to get the wrong answer for the resistor? Am I going to get the wrong answer for that 9-volt battery over there? I don't know. Let's think about it. What if I want the voltage to be the X, and I want, the Vs will be the X, and I want the current to be the Y? Can I manipulate this equation to make it the other way around?
Vs minus V over R.
Yeah, I mean, the goal would be, if I want the I to be the Y, okay, so this is kind of an aside here, right? What if I want to switch the variables, right? And I would say this would be to match the real experiment, right? Because I would argue that in the real experiment, this is what I'm going to do. Hook up this and measure that. So switching the variables, does it literally mean I'm interchanging the letters? No. This relationship is the physical law, right? I can't just switch the V and the I. Right? This law has to hold. This law holds no matter how I write the algebra down, yes? So if I want the I to look like the Y, then where should it be? Other side of the equation, right? So isn't it true that if I solve this thing for I could show some steps in between, but I want you to get the hang of whenever you can efficiently do algebra, you ought to, okay? Because there's a lot of it in engineering. Okay, so I, solve for the I. You already said Vs minus V, you divide by R. Okay, so what would I have here? 1 over R, right, times the Vs. What about this guy here? Yeah, and then it's minus V divided by R, right? Isn't that what the equation looks like if I just rearrange it? Okay, and you know what? I don't even like this word. This is too, switch is no good. Rearrange is what I'm going to use instead. Okay, just to be clear. So rearrange the variables, okay, to match the real experiment, okay? Because that's what we've done. All right, so great. So if I look at this now, then take a look at it. This is y equals mx plus b. Okay, and so I can still use the same idea, right? But now the y is the current, right? It's the output now. How about the m? What's that? Yeah, it's the reciprocal. It's the 1 over r is the m now. How about the b? Is this bothering you? Is the b the I? Is v over r the b? Negative, right? Because negative, you know, there's no such thing as negative. Negative is plus, minus, right? So now it looks a little closer, and isn't it true that the b is minus v divided by r now? So the point is, I had a question before class, like, can you talk about, you know, how do you know what's the independent, what's the dependent variable, okay? In engineering, it's up to you. You're the one with the model. You're the one with the experiment. You need to make a decision of the way you want to make the algebra look. Once you make that decision, if you're going to use methods to find the equation of a line that are based on the slope-intercept form, y equals mx plus b, y is the dependent, x is the independent, I could do it either way. Right? So this looks a little messier, right? Maybe why we did it the other way first. But the physics better not be any different than this, right? So it means that if I apply the same data points and do this, the value I get for the resistor had better be the same number. Let's give it a try. All right? So the slope, right? Isn't the slope m, right, is equal to delta y over delta x, okay? And so that means that in this case, right, that is 1 over r, right? 1 over r is, what's y now? I. So it's now the change in I divided by the change in Vs. Now look, you can see that this one's going to work, because before we did the r, and the r was Vs divided by I, right? And so now 1 over r is the thing upside down. Okay, so you can see ahead of time that this will work, but let's run the numbers anyway. So it's 1.1 minus 0.1, right, divided by delta Vs, which is 20 minus 10. Okay, and so this number is what? 0.1, right? 1/10. So if 1 over r is 0.1, right, then that means r is equal to what? R is still 10 ohms, right? Now, the equation of my line is not going to be the same, okay? because this is my slope, right? This guy right here is the m for the equation I'm talking about. It's the reciprocal of the other m. All right, and then so what about the intercept? How do you find the intercept? I need to write what I have, right? I is equal to 1 over r. That's 0.1 times vs, right? Plus minus v over r. That's my b. How do I find the minus v over r? Yeah, I put in the numbers. So again, using one of the data points, right? And the x is now the vs, and the y is the I. So vs comma I, use whatever numbers I want, 10 and 0.1. Okay, and if I plug those guys in, then according to this, right, I, which is 0.1, is 0.1 times vs, that's 10, plus the minus v over r, which is my b. So what do you get? Can somebody give me in one calculator punch, minus v over r is equal to what? This is 0.1. 0.1 times 10 is how much? 1. Move it over here and you get negative 0.9. What happens to the negative? It cancels out. Okay, better cancel out because we already knew the answers before, right? And these were not negative numbers. Okay, so minus v over r is negative 0.9. Okay, and so with this equation right here, okay, instead of this, vs is 10i plus 9, what I just calculated is I is equal to 1 over r vs. 1 over r was 0.1. 0.1 vs plus, right, minus v over r. Minus v over r is minus 0.9. Okay, incidentally, if I wrote the equation like that, what would be the units on it? Yeah, this is now amps. Okay, that's it. Okay, and look, how do you know this is right? Look at the equation above it, right? Solve for I. Move the 9 over, divide by 10, and what do you get? You get this, right? So we didn't need to start from scratch. The reason we started from scratch, okay, is to let you know that the independent variable, the dependent variable, it's up to you. You set up the experiment. You have the model, okay? When you apply the math, you write the model the way you did it. If it's on the left side, and you're using y equals mx plus b, then whatever's on the left side is your dependent variable. It's that simple. It's up to you. Questions on that? All right, so one of the things we try and do in this course is break down your dependence on y equals f of x. Okay? Once in a while, we use that notation for things in engineering. Usually, we use things like voltage as a function of current, velocity as a function of time, sometimes y as a function of x, not usually. Okay, so don't feel constrained by that. Think about what's the big picture, what variables in which place, and then draw on the algebra skills that I know you all have. Okay. All right, so that's enough on lines. Going to move on to quadratic equations briefly. We got about 25 minutes to wrap that up. What's a quadratic equation? Let me see a hand here. Who knows what a quadratic equation is? Anybody? For every input, there's 2 outputs. That's a feature of a quadratic equation. Okay. What is one? If I see an equation written down, how do I know if it's a linear equation or if it's a quadratic equation? Second derivative. Second degree. Degree what? power of 2, second degree polynomial, the word you're looking at. Okay, so it is one function, one of the variables, right, depends on the square of the other variable, and it might also depend on the first power, et cetera. Okay, whenever I have an algebraic equation where one of the variables is squared, I'm now living in the world of quadratics. Okay, so quadratic equations in engineering. Okay, and so we'll do this again by pure example. We just finished electricity, so let me go back to kind of a mechanics type problem. So here's an example from physics. This is physics 2400. One of the things you do in general physics 1, okay, initially, is particle motion. We do this again in dynamics, ME 2210 dynamics also. Okay, and so it's a particle motion problem. So let's take a look at a projectile, okay, in the vertical plane. Okay, and so what I mean by that is not a projectile, say, thrown across the room. Okay, but what I mean is something going straight up and down, okay, like this, so that I can measure the height, h, as a function of time. Okay, and let's say that that projectile's height, h, as a function of time, is the following. 96t minus 16t squared, and we'll do this one in English units, feet. Okay. Let's ask a few questions about that. Okay, making the point that h of t, this is the height, right, as a function of time. That's it. So t, that's time, okay, and that guy's in seconds, right? The height's in feet. All right, so several questions I want to ask about that particle motion. Question number 1. What if I want to find the time when the height is a specific number? Okay, say 80 feet. Okay, so question number 1. Okay, let's find the time t, okay, when h of t is equal to 80 feet. Help me out. Set the equation equal to 80. All right, so h of t, okay, is equal to 96t minus 16t squared, and I want to find the value of t when that equals 80. Okay, so that's it. So, any suggestions on how to solve an equation like that? All right, so you give me a specific step here. Can somebody talk about it from a strategy level? What's the goal here?
Isolate t.
Isolate t. All right, so in the end, I want an answer t equals. All right, yes? All right, get everything on one side of the equation is what I would say the strategy is. Okay, so this works, by the way, in general for solving equations. Okay, good idea to try and get everything on one side, get the other side 0. Okay, there's a reason for that. All right, so everything on one side, you can think about it as this one here, those ones there. In my head, I'm going to look at this and say 16t squared over there minus 96t plus 80 is equal to 0. Does that look good? Well, so what I did here is I moved the 16 over there, right? So it's positive. And then I moved this over there also, so that one's negative. Okay, the other way to think about it is I leave this one here. I move the 80 over, so now the 80 is negative also. And I multiply the whole thing by minus 1, and I get this. Are we good on the algebra here? Yes? Yes? Good? Okay, so here it is. And so, great. What else? How do I solve an equation like that for t? All right, so we got some options. So first of all, what kind of an equation is this? It's a quadratic equation. Okay, it turns out that it's in a standard form here. Okay, now, before I solve any equation, if the right-hand side is 0, I can always look to do what? see if I can reduce it down. So if I got a common factor, I can just get that out of there right now. Can I divide through by anything? 16 divides right out of this. So this is nice. So I'll have t squared minus 16 and 96 is what? 6t, and that means this guy's got to be what? Plus 5 equals 0. Okay? So there it is. This is a quadratic equation, okay, for t. Okay, that's it. Okay, incidentally, it's a pretty bad 5. Let me fix that. 5. Okay, so quadratic equation for t. What is the most general form of a quadratic equation? Somebody want to think about that? Yeah, ax squared plus bx plus c equals 0. In fact, again, we pirated the page out of the inside cover of your calculus book, right? And it just, this is what the calculus profs that write the calculus book have decided is the most useful stuff from algebra and geometry, and they put it all on one piece of paper. Okay, so good idea to think about, I probably should be able to do this stuff. And so if you look on here, you've got this kind of thing there. I mean, there's a place where they talk about the quadratic formula, and they talk about the form ax squared plus bx plus c equals 0. Okay, great. So that's true. There's more than just the quadratic formula. Okay, I would argue that there's 3 basic ways we want to be able to solve quadratics.
I don't know what it's called, but we put like a negative 5 and parentheses and the other thing.
All right, what is that called that he's describing? He's describing how to solve it. Say, factoring. All right, so great. Let's do it all 3 ways. Okay, so method number 1, we're going to call this factoring. Okay, if you can see right away how to factor something and you can do it with whole numbers, this is the fastest way to solve a quadratic equation. Okay, and so the goal of factoring is to do what? What he said, yes?
Break the equation apart.
Break it apart so that you have what?
You have 2 smaller equations.
Okay, and are they added together or what? They're multiplied. Okay, in general, quadratic equation or not, when the right-hand side is 0, it would always be nice to express the left as the product of several terms. Why would that be nice? Sorry, one more time?
All those terms can equal 0.
Right, so if any one of those terms is 0, then I have an answer. All right, so that's the goal. It's a strategy, right? So let's see if we can multiply things to get 0. So factoring is, can I write this like this? 2 factors equals 0. Okay, and when I multiply these 2 things out, how many different things are going to be in here? There's 2 terms in there. When I have 2 terms added together, we call that a what? That's not wrong. Sum. So binomial is the word I'm looking for. Okay, and so when I factor this thing, right, I want to have a t, right, in this one, and I'm going to need another t over here because when I multiply them out, I need to get a t squared. Right, so we know we're going to have some t's, right, and so the question is, what do I add or subtract from the t's in order to get this? All right, so instead of just shouting out the answer, because there's definitely people in this room that know they learned this like in 10th grade and have no remembrance of how to factor anything. Can somebody give me a strategy for how to factor? What am I looking for with these numbers? Good, yellow, yes?
What multiplies the base from 5 and adds together gets you 6.
Okay, why am I looking for that? He said what multiplies, what are the factors of 5, okay, and do those factors add up to give me a 6? This one's a relatively easy example, right? But why do you want to do that?
You have to foil the factor.
All right, so he said FOIL. Raise your hand if you ever heard the word FOIL before. So this is interesting. International students are not raising their hand, right? So, and it's an American thing, right? So FOIL is what they say, with the front and the outer and the inner and the last. It's the way you multiply a binomial, right? But you start here, and essentially it's just the distributive property times each term, right? This one times these 2, and that one times those 2, and every term gets multiplied. So when you do that, to get the last term on the end, right, you're having the factors, but then the terms with the t's get added together when you perform that expansion. So you're looking for things that when multiplied give me 5, and when added give me 6. What are the factors of 5? 5 and 1. It's a pretty easy one. Do 5 and 1 give me 6? Heck yeah, as long as these are what? Negative. Okay. See, so not all factoring is hard. By the way, if you have to think much more than this to factor something in an engineering classroom, don't bother. Okay, so we have other methods. So factoring is like, oh, that's factorable, bam, answer. It's the fastest way if it's obvious to you. So it's a useful skill set. So these two numbers should be what? 5 and 1. So t minus 5, t minus 1. How do I know those numbers are correct?